Hey everyone, this is Jonathan from Chegg Tutors, and this lesson is about electronegativity of atoms, which is the tendency for an atom to attract bonding electrons towards itself when it's in a bond with another atom. So you can think of it as the tendency for an atom to be greedy for electrons. So when it's in a bond, if it's more electronegative, it's going to pull and hog those electrons, making itself in an electron-rich environment, while the other atom is in an electron-poor environment. So what causes atoms to be more electronegative than others? Well, it depends on two factors. The first one is the atomic number, which is the number of protons, which you can think of basically as just positive charge, which is going to attract negative charge, which are the electrons. So the more protons something has going across a row in the periodic table, we'll see it affects the electronegativity. And the other factor that affects electronegativity is the distance of valence electrons from the nucleus. And the valence electrons are the electrons involved in bonding with other atoms. So if they're really, really far away from the nucleus, it's hard for that atom to pull bonding electrons towards itself and be an electron hog. So now let's look at the electronegativity trend going across a period in the periodic table. This is period number 2. I excluded the noble gas because it's very stable and doesn't involve itself with bonding, so we don't need to consider its electronegativity. As you go across a period, you're increasing the atomic number, we can call that Z, by 1. So that means you're increasing the number of protons found in the nucleus. So lithium has a +3 charge, beryllium has a +4, and so on down the line. But as you also go across a period, you're not increasing the valence electron shell. So lithium has its valence electrons found in energy shell number 2, and so does fluorine. And that dictates the distance between the valence electrons and the nucleus. So if you have the same energy shell, you have a similar distance between that and the nucleus, but you're increasing the positive charge. So as you go from left to right, you're not changing the energy shell, which dictates the distance between the nucleus and the valence electrons, which are involved in bonding, but you're increasing the positive charge. So as you increase Z, which is the number of protons found in the nucleus, you pull bonding electrons inwards, because the valence electrons are the electrons involved in bonding, and if you're increasing the positive charge within the nucleus, you have more of a tendency to pull them inwards, because positive charge attracts negative charge. So if you're not increasing the distance between the nucleus and the valence electrons, because you're not changing the energy shell which they're found in, and you're just increasing Z, which is the number of protons found in the nucleus, you have a tendency to pull those electrons in towards yourself because you have more of a positive charge within the nucleus. So as you go from left to right, you increase electronegativity. Because fluorine has +9 in its nucleus, lithium has +3, so fluorine is going to pull bonding electrons in towards itself more than lithium would. So now let's look at the electronegativity trend going down a group in the periodic table. I chose group number 17, the halogens, and I only chose 4 of them. So we obviously see that you increase Z, which is the number of protons found in the nucleus as you go down a group. So fluorine has +9, chlorine has +17, bromine has +35, and iodine has +53. However, as you go down a group, you're increasing the energy shell that the valence electrons are found in. So fluorine's valence electrons are found in energy shell number 2. So energy E shell equals 2 equals 3 equals 4 equals 5. So as you go down a group, you're increasing that distance of the valence electrons from the nucleus, which has a much more profound effect of increasing the atomic number. So as you increase that distance, it's harder for the nucleus to pull in bonding electrons towards itself. So it's less electron greedy. So as you go down a group, your electronegativity decreases because iodine has such a huge distance from the nucleus to the bonding electrons, the valence electrons, that it can't really be electron greedy. It can't pull them in as well as fluorine, because fluorine has such a small distance between the nucleus and the bonding electrons that it can really pull those bonding electrons in when it's in a bond with another atom. So it increases going up a group. So you can probably see based on the last slide and this one that fluorine is your most electronegative atom. So we can put the trends in the periodic table. So we found that as you go across a group, it increases from left to right because you're not changing the energy shell that the valence electrons are found in, but you're increasing that atomic number, which pulls those bonding electrons in more. So increasing electronegativity. And as you go up a group, you also increase the electronegativity, because when you go down a group, you're increasing that distance between the bonding electrons and the nucleus, which decreases the tendency of those atoms to pull the bonding electrons in towards itself because they're so far away. So now let's look at an example. Hydrochloric acid, H bonded to Cl, hydrogen bonded to chlorine. So chlorine is found in the upper right of the periodic table, so it's very electronegative. Hydrogen is not very electronegative because you can see where it's located on the periodic table. That's not an electronegative area. So chlorine is much more electronegative than hydrogen, which means chlorine is greedy about the electrons found in this bond right here. So chlorine's going to hog those electrons and pull it towards itself, leaving hydrogen without much electron density. So hydrogen is going to be in a very electron poor environment because chlorine is going to pull electrons towards itself, and this is going to leave chlorine with a partial negative charge because electrons are negatively charged, and if chlorine's pulling those electrons towards itself, it's going to have a partial negative charge. And this is going to leave hydrogen with a partial positive charge because it's now an electron poor environment, so it has a less negative charge or a more positive charge. So we can also illustrate this by colors. So they normally demonstrate electron-rich environments with red and electron-poor environments with blue. And this causes molecules to be polar because they have two poles, a partial positive pole and a partial negative pole. So HCl, hydrochloric acid, is a polar molecule due to the differences in electronegativity. So whenever you have molecules that have different electronegativities, which means that one is going to be hogging electrons over another, you have the tendency or you have the capability to be a polar molecule. So I hope this helped and showed you about electronegativity. My name's Jonathan and I'm on Chegg Tutors.